Welcome to our course on fundamentals and biomedical application of quantum science and engineering. This is a course that is being organized to give you some concepts that are important in many fields of science and technology today. Myself, Vanderlei Bagnato, and Professor Yakovlev are going to work with you to provide you some ideas, some main features related to this important topic of quantum science. You already hear about quantum science, right? This is not a new word. Sometimes quantum is a word that's everywhere, even in the news nowadays. But we do not learn the fundamental part of it that help us to contribute to development of this field inserted in many of the technological areas. Biomedical is one of those areas where quantum science is being growing in importance and also in challenges. So the use of sensors, the use of nanotechnology, many other examples are dependent of quantum concepts. And that's the reason why we put together a course to give you the fundamental part of it. Try to give you some intuitions. You know, we don't want to be a heavy mathematical course that you can take in other places. But this is supposed to be a more discussion type of course where the main ideas should go across. Okay. So before we start that type of course, it's nice for you to know where are you boarding. So what we are thinking of presenting to you during the course. So that's why this first lecture, I'm going to explain how we're going to run the course. Independently, if you are biomedical major or electrical, or electronics, or computer science, or even biologist, or even physicist. We're going to follow some general ideas to give you the concept. Okay. Well, the first question that you may ask is why we want a course like this, right? So I hope you are in the right course, so fundamentals and biomedical applications of quantum science and engineering. You know, the original title has an engineering because, you know, everything we do in application and everything like that, we have to do engineering. So engineering is quite fundamental. And of course, we call biomedical engineering, but, you know, you will understand what I'm talking about. Okay, so the first thing is let's give to you this general information, and let's start by saying why. Why we put together a course like this? Why somebody wants to learn quantum mechanics in the present situation of science and technology? Okay, well, to explain this, let me tell you a little bit of history. On the 19th century, we developed many machines, you know. Before we have a lot of horses working for us, but suddenly, on the 19th century, we start to developing machines. And today, we more or less have a consensus to classify the 19th century as the center of the machine age. So we learn how to use mechanical power, we learn how to use electrical power, we learn how to use many things in your favor to grow up civilization. Okay, so, and for that, many scientists, if you look at the science around in the 19th century, many people were thinking about machines, were thinking about how can we convert heat into mechanical power and so on. That was a very interesting age that pushed us towards a tremendous development, right? Okay, but then time goes by, we reach the 20th century that just ended a few years ago. So we were in the 20th century, And we learn so many new things. You know, we learn to communicate each other. We learn to connect the world. We learn to use the internet. We use it to be everywhere all the time. Okay, even though that violates some principles, but you know, it's not important. We learn to communicate. And we develop too many tools. You know, TV, radio, everything that's supposed to transfer ideas were developed on the 20th century. And, you know, many people classify the 20th century as the age of the information. So the 20th century went down to history as the information age. We really connect everybody. And today, of course, we are making use of this development that happens during the 20th century. But now comes the 21st century. We reach the 21st century with many challenges. You know, we have to learn so many new things. We have to learn how to really take care of civilization, in case of healthcare, of course. And then we start to understand that most of the solutions cannot be done by just trying and trying. We have to learn about the micro world. Nanotechnology came like strong. Well, was already quite strong at the end of the 20th century, but became a kind of crucial for the 21st. And then when you go to those scales, you know, new concepts has to come. And here comes the quantum. You know, not only that, but today you can turn on the TV and people are going to say, well, the new development of quantum computer, you know, quantum information, and many other things. We already speaking about the quantum biology, you know, like real quantum phenomena that are important for life. We all know that at the very slow scale, or sorry, in the very small scale, things are quantum. But we have to understand how important is that, how that determines the way life is progressing. And today is almost like a consensus that the 21st century is classified that will be the quantum age. What means to be classified as a quantum age? Will be an age where the quantum effects will dominate many things that we do. In this age, in the 21st century, we must use quantum mechanics and maybe even understand a little better things that we do not understand. But the most important is now that's going to be part of our thinking in the day-by-day basis, so we can really overcome new challenges. Can you imagine? We have to go to the atomic scale to understand how a virus works. You know, all this process of getting close. We design the medication on the molecular level. We design materials on the molecular level. You know, we want to reach space, so you have to come with new materials that nature does not, you know, they are not giving to us by free. Some materials that we have to artificially make up. So everything depends on atoms arrangement. Everything depends on architecture that we did not know before, and they depend on quantum concepts. So everything really indicates that we are reaching the quantum age. So if we are reaching the quantum age, it's better that everybody that's involved in health, in technology development, and many other fields learn about the principles. Okay? Up to now, quantum mechanics was something more on the domain of physics. We cannot do physics today without concepts of quantum mechanics. But we understand now that quantum mechanics goes beyond physics. It is in nature. Nature is quantum. We cannot avoid that. You know, quantum, we believe, has to be, it will be, part of our culture. It is already. Most of you do not know that some of the information is being transferred from place to place in a quantum type of base. But I think, things are getting stronger. It's each time we are in a level that the quantum phenomenon is important. Things that are coherent, things that are, much beyond the classical intuition or the classical concepts. They are important now. We are learning, key and lock type of things for all this biological structure, but people know that the main development comes when you really understand the chemical bonds on the quantum level. We really understand how structures are formed in those molecules and everything. In this context, of course, it is special for fields like biomedical engineering or computer science or many others to know the concepts. Otherwise, you'll not be able to even read some manuals in the coming future, because many devices that we're going to use is going to use those concepts. And we know that to talk with a machine, we must understand it a little bit. On the top of that, we have machine learn. Machine learn is something that we should read things while they're happening to be able to interfere and optimize things. And that, I believe, will be involved in the life metabolism. We'll be able to teach machines to really optimize things, to heal a kind of wound, to really repair the neural system, to do all kinds of things. We're gonna have to reach that concept. Well, so you see, everything is indicating that we must know about quantum mechanics. We cannot only know the word quantum mechanics. We have to know in what basis it's sitting. We have to know what are the intuitions that we have to have. It's like thinking in the classical way. Can we just continue to think, or if we know that quantum mechanics do not complement classical, but substitute classical, we may be able to really interact better on the development of new concepts and new technologies. So the main goal of this course, therefore, is to transmit to you intuition. Because the best thing is we have to understand how things goes around us or what concepts are involved. You need to have intuition. You have to understand how the quantum mechanics behavior in a way that you can think about those concepts and understand the main applications. So that's basically what we want to do in this course. Give you the concepts, how mankind learn about quantum mechanics, how nature revealed to us those concepts. They came by free. We had to think hard how man was that smart to imagine what we consider today the most important theory of science around the last century. Quantum concepts. That's it. That's the theory that's the most important one. We could not understand the DNA structure or anything if you are not able to understand how the chemical bond, how quantum mechanics is determining where chemical bonds should be. Why we have only a finite number of structures in nature. We don't have a lot. If you take materials, they are all classified in a few Bravais lattice structures. So we have a few basic structures. Is that determined by quantum mechanics? We have to know that, right? We work with that every day. Okay, so we're going a little beyond just the technical information. We're getting into some concepts. And I hope you enjoy the course. This is a course to enjoy. It's not to be hard. It's not a course that you should, oh boy, now is the lecture. No. You should say, wow, now is the lecture. I'm going to learn some new things. And this is what we want to transfer to you. That's the concept we wanted to transmit. Okay. Well, the course is a regular course, so we must have some ways you should follow some rules. So we're gonna have 3 lectures a week, more or less in average. Sometimes we have some holidays and things, but in average we have 3 lectures a week. Most of them are online lectures, but we should have some presential lectures in the coming future. As the situation give us conditions to do that, we're going to have presential lectures. Okay, and as you know, this is a course. I am a Hagler Fellow in the Biomedical Engineering department, but I am also a full professor in the University of São Paulo in Brazil, and therefore we are seeing the both symbols here. But consider now as part of both, because we want you to give a concept that goes much beyond any place. Okay, so we're gonna have 45 lectures basically. During those 45 lectures, as I said, most online, we should give you all the concepts that we want to give you. We want to justify things, we want to introduce new ideas, we want to explain. Of course, we do need to do some mathematics, because the way to express nature sometimes we can do by concepts, but to go deep in this kind of thing, we must do a few calculations, but those are calculations that any freshman in science in general should be able to do. We're not gonna go deep in with strange solutions, mathematical solutions, or require that you know very, very deep concepts to understand what we're going to talk about. So the level of the lecture should be very accessible to undergraduates or even beginning of graduate students in any field, even out of the health or of the exact science. The quantum concept is something that part of our life we should know if you want to understand many things. Even the evolution of man may be very well related. People are finding today that the way we develop our senses or many of the things we have are related to quantum. And of course, the universe around us is very quantum. As in nature, as you've seen by the recent Nobel Prizes, that they understand even better how gravity, how particles, how everything is happening, and that has a lot of quantum on it. Okay, now, giving the lectures, we need some return from you, and we're gonna do that with problem sets, right? So we're gonna have 10 problem sets along the course. 7 of those problem sets you're going to do by yourself, individual, and 3 of them can be done in group. So you can get clustered together with some friend. Those are not to be done individually, because we want to stimulate the discussion. So it has to be done by group of students. And then there will be a term paper. A term paper through a seminar. We're gonna give you a topic, and we're gonna see, this guy or gal is in bio. Okay, so let's give a topic that he can apply. He can, somehow give us a very short seminar, think about a topic and give us some seminar to discuss the concepts that are involved. So that's why we're going to distribute the topic only at the end, when we learn who is taking part of this course and everything. Okay, so this is mostly the structure, right? You should receive the lectures, the address to log in and to see the lecture. And you should receive also the problems, the activities, and you don't need to take notes of what I'm writing in here. That's also be available to you. So all those notes will be available to you. So we're gonna give those notes to you. You can have in the computer, you can follow, because otherwise you'll be trying to take notes, and I hope you pay more attention to us than keep writing. So you can, of course, complement information, because we speak more than what we write, and therefore you should take some notes the way you understand things, right? And you can do that. Of course, you should have a notebook. Everybody should have a notebook to take notes. But those basic comments and readings that I'm presenting here, or the notes that I present in the lecture, will be available to you, lecture by lecture. Okay? They are like 7 to 8 of those pages with those notes, and of course they are put in a way that you can follow up and understand the structure. Okay, so I hope with this we told you more or less how is the course, how we're going to evaluate you, and the overall context of this quantum business, because it's really important. You know, sometimes you're going to see that nobody knows everything about quantum mechanics, right? So that's why it's very interesting to teach to everybody what we know, because it means that we have a chance that some smart mind will come with very new ideas, very nice ways of explaining things. Okay, so let me explain the structure of the course to you. So, you know, this is in this general lecture, this first general lecture is for you to know what is going to be. And then the next lecture, we already start to give you the ideas. First of all, I want to put to you the importance of things, right? I mean, I keep telling you that quantum mechanics is everywhere. We know that the universe is mechanical, you know, we have been publicized a lot of the mechanical universe. You know, Professor Carl Sagan, you know, he made a wonderful science diffusion of the mechanical universe. Actually, it is mechanical, but it's also quantum, right? So you have to understand that many things around us happens because of quantum mechanics. And then I have to tell you this importance. I have to start to highlight some of the things that goes around us. So in some sense, you can develop your perception if you do not have yet. Then we're going to have an introduction of importance. So we must speak about the importance of quantum mechanics. We should speak about where is it? You know, where should I have it more clear? It is that in the very small micro world, or is in the macro? Is in the my size type of effect? We have to pay attention to things, and most of the things we never thought was quantum is fully quantum. People are discovering today that's fully quantum, and we have to, if we want to understand it, we have to know, to admit. Okay, you see, when people started to discuss the quantum mechanics to replace classical mechanics, they try to hold themselves in concepts that was available, right? And even though most of the things that constitute the matter we classify as particles. Particles in mechanics is the one that has mass, or if it does not have mass, has momentum, or mass and momentum, sorry. But to explain quantum mechanics, you have to go beyond that, you know. That was a vision and well-established theory by Newton. But people realized that some effects were not really consistent with that. And waves, sometimes quantum mechanics is called wave mechanics too. Then we have to learn some bases about waves, because they will be important concepts for us. You know, we're going to deal with things that normally we believe are particles. They belong to the class of Newtonian type of object, but they cannot explain the phenomena that we observe. We have to go to waves. Waves are some interesting things, because waves, you know, you're going to see the concept of waves. We're going to have a full lecture of waves to somehow review the main concepts. You know, I'm going to stick myself with mechanical waves, but electromagnetic waves are the most important waves we have around. And people learn, well, you know, when people discovered that the light was waves, that was a big success in many things. They start to explain what was going on. They start to explain the observations. They start to not be in the darkness with light. So we're gonna review some of that. We have when we're gonna speak about the waves and everything, we're gonna have to speak about probability. Probability is something, because in quantum mechanics, you have a physical system and you have the detection of the physical system. And you need to find ways of describing this physical system. How are we going to do that? How are we going to put some mathematics? How are we going to put some interpretation on this? And then we have to learn some about probability. I know that you are very familiar with probability concepts, but we're going to have to do a little more, go to the continuous probability distribution. Just if you know, it's never a waste of time to review. If you don't know, it will be a new concept that you're going to learn. But we do need to expand the 1 or 1.5 lecture on concepts of probability, because we're going to use that. That will be very important on the interpretation. As I said to you, we're going to always have a system, a physical system, that we learn how to describe, but we have to interfere with that. So we have to know what's the language, and probabilities is one of the interpretations of quantum mechanics. It's very, very, very important. Without it, we'll be in deep trouble. So we're going to make a small revision on probabilities. Probabilities, there are many ways. There is a discrete probability, which is like individual events. We're going to quantify if one thing happens or not, or in what way it happens. But there is also continuous probability. Those are things that happens in a continuous way. Depends on variable that continue varies. That's very common for systems like us. We are continuous probabilities of things because we are made of so many atoms and molecules that many, many properties can be around. Basically, you can go from one property to the other, like the velocity of the molecules or everything, and it's very tiny variation from one to the other. It's not discrete. And then we have to learn the concepts of continuous probability. And for quantum mechanics, in time and in space, the concepts of continuous probability, it turns to be quite important, and we're going to have to use it. So you see, in these, let's say, general ideas, we're going to go for the waves. So that's the first thing we're going to do. And remember you of things that happens to waves, how they behave, how are the equations, how can we describe waves, what are the important properties of waves, right? Is like the same importance of one particle moving like Newton, or they are different? Okay, we're going to do that. And probability. So those are the two review parts that, believe me, if we review that, if we understand that, we go easier on the concepts of quantum mechanics. But learn that we have to start to see how the quantum mechanics concepts start. Quantum mechanics is something that, if you ask anybody around, is a theory, they're going to say, yeah, it's a theory. And is mostly dominated by theoreticians, they're going to say, yeah, it's mostly dominated by theoreticians. But, quantum mechanics is wonderful. They say it's the most important concept and theory that was born in the last many, many decades, and was born by experimental observation. You have to understand that when you ask questions to your mind, this is only theory. But when you ask questions to nature, this is reality. It's things that are there, and we make interpretations. So what we call quantum theory actually is some concepts that were constructed to understand the answers that nature is giving to us. It's not answers from our mind. It's we observe. From the observation, from the reality, we need concepts to explain. So we're gonna have to learn this type of thing. How mankind idealize these concepts, how they come put together ideas. And then, of course, we have to describe many experiments and how de Broglie came with some hypotheses that are fundamental for the understanding of those concepts. Okay, once we have learned that in a collection of lectures, then I hope you'll be convinced, because scientists normally are convinced by observation, right? Those are facts, not suspicions. Maybe the explanation is a hypothesis, but the fact is the fact. We're going to give you the facts. And then comes the hypothesis of de Broglie. Try to explain. But then we're going to start to construct the toolbox that we use for the quantum mechanics, right? We have to start to construct the ways of dealing with the problem. So you have to introduce what is this matter wave, which means a wave made of matter, mass, charge, and things like this. And then we have to understand that we cannot give up what we know. You know, I am here, sitting here, I have to be here. If you see a tennis ball flying around, can I describe that with quantum mechanics? If I do, I have to understand why I see the ball localized, design a trajectory. This was a great investment and a result in quantum mechanics that was given by Heisenberg. And it's called Heisenberg principle. And of course, you know, one concept takes to the next and so on. If we understand well this, with the basis that we develop on waves and probability, we're going to be able to understand why energy is not a continuous in the quantum world. We're going to see the quantization of energy and how important people generalize concepts, because this was built up block by block. Quantum mechanics understanding, or quantum mechanics box 2, was like created along many discussions. Okay, so once you do that, you know, we have to come and explain to you the construction of the master equation that we normally call Schrödinger equation or wave equation. So we have to do that and do some applications, so in a way that this will make sense to you. You know, we have to, first of all, the equation has to make sense to you. And we need to help you to understand. It's not an equation that you can deduce, but it's an equation you can construct. And that has to make sense based on things that we know, especially energy conservation and everything. Those are concepts that are reality, that are truth, that nature places for us, and we have to use it. Okay, once we construct those master equations, then we go to really the real world of quantum, going to molecules and energy, the mystery of structures. So we go to really concepts that are everywhere on us, right? So we're gonna really apply this so you can understand why things are the way they are based on those concepts that we built before. And then light-matter interaction, because everything we do is observations, right? So we must let the light interact on the quantum level. On the quantum level, we must let light interact with the matter, atoms and molecules, and understand what response they are giving to us. What is this? Why is light so important for everything? What's the connection? And then, of course, here is where we start already applying. Because biomedical engineering, for instance, or even engineering, they depend a lot on light-matter interaction. Basically, very little instruments do not have that concept on it. Either you do mass analysis or you do spectral analysis. It's very hard to get out of this. And when you do spectral analysis, you either do frequency domain analysis or time domain analysis. So we must understand this, because that's the way we learn things. In fact, all the fundamental part of quantum mechanics came from those applications, came from learning how light interact with atoms and many things. And then there is some concepts that are fundamental for life science, which is tunneling. Tunneling is something that belongs to quantum mechanics. It cannot have any analog anywhere in classical. Because some of the things we can always find a little bit, import a little bit intuition from here and there. But tunneling, I'm going to explain what it is, and you're going to be amazed because there is no such a thing in classical. And that happens all the time in your body, happens all the time in nature, helps all the time everywhere, even in the lamps, the LEDs that are illuminating this room, everywhere. The screen that you are watching, many things are having that. Okay, then we go to more applications. Because, you know, once you understand the concepts, it's nice to correlate them with many things that you observe in a day-by-day basis. So we go to many applications, including applications in biology, including applications in nanotechnology, and many others that will come around the course. You know, I let here many question marks because applications appear every day. Every day applications appear. I just before this lecture, I was looking at my computer and I saw some news about new understanding of X-ray interaction with cells on the molecular level, of course. And can you imagine how important is this for radiotherapy, for instance, which is a tool very important for us, or even development of structures on the living objects and everything. That's interesting. Okay, so what I explained to you is how the course will be done. Now that we have that, you know, you are prepared to board in, and we go in this trip, trying to understand a little better those quantum phenomena. See you in the next lecture. Bye-bye.